8 o'clock early this morning? Yeah. It's kind of early anymore. All right. The good news is we had a break. The bad news is we have to hit it pretty hard here because there is an exam on Wednesday. I don't want to cover anything new today, but I do want to review what material we have. I've posted 2 old exams. I haven't posted the solutions. I've posted a study guide. The study guide is pretty much the same thing here, but in more detail. And I've got a couple example questions that just are additional things that I might ask. So there's any number of ways I could go forward, Joshua.
The two past tests that you put up in Whitworth, do those follow the same material we have here, or is there extra on them or less on them?
There's really, I think we have a pretty close parallel between those exams and where we are right now.
Okay.
So, last exam I think we were a little ahead. I think we're just about on par with where we were the last 2 years. So I think that you'll see consistency there. Any other questions? So, if I gave you the potential, either mathematically or graphically, could you calculate the electric field of James?
I have a question. Is there going to be any symbolic stuff?
I could. I mean, I like, certainly, if you are a good physics student, solving things symbolically typically makes your life easier. Right? So even if I don't explicitly ask you to solve something symbolically, oftentimes, not as much in physics 2 because the problems aren't quite as involved, but certainly in physics 1, certainly in physics 3, the more symbolically you solve your problems, the better off you are. So even if I don't explicitly ask for it, it's usually better. Some of the instructors in the department, if you don't solve things symbolically, they'll check to make sure your units are appropriate in every step on the way, and will deduct credit if you don't. And that's usually challenging to do, to keep your units straight at each step in your work. So that's a good question. I encourage you to solve some things symbolically. It tends to make your solutions better. Any other questions? Right, so, there's potential to electric field. There's 2 ways I could go. I could either show you things graphically, and if you look at the old exams, I could ask you to solve things graphically, or I could write them down mathematically. So can you go from the potential to the electric field back to the potential? To calculate the potential, we have an integral. So there needs to be an integration, constant of integration. If I just talk about what is the potential. So there needs to be some reference point to that potential. If we're talking about a point charge, where do we typically decide that reference point is? Joshua? Infinity. Very, very far away, the potential is 0. If we have a positive charge, as we get closer and closer, the field becomes more and more, the potential becomes more and more positive or negative. Really hoping. All right, so it's been a good break. We need to definitely catch up. If we get closer and closer to a positive charge, the potential gets higher and higher. If we get closer and closer to a negative charge, the potential gets more and more negative. What happens to the potential energy? It depends on the charge that we're bringing. So if we have a source charge that's positive or negative, or a combination, let's start with the positive charge. As we get closer and closer to that positive charge, what happens to the potential? The potential increases. If I have a positive charge and I get closer and closer, what happens to the potential energy? Does it go up or go down? It goes up. If I have a negative charge and I bring it closer and closer to a positive charge, potential energy goes down, the potential goes down. If I bring a negative charge closer and closer to a negative charge, does the potential go up or down?
Up.
Potential goes down, potential energy goes up. All right? So think through those. If I give you a motion of a particle in a field, last exam I was most likely to ask you something related to kinematics. At this exam I'm most likely to give you a question that you can solve most easily using potential energy. All right? So the key thing is our change in energy will be equal to the charge times the change in potential. So don't do kinematics if possible. All right? Look at the change. If you know the potential at one place, you know the potential at the other place, then you should be able to determine the change in energy. If you know the charge, you know the change in potential energy, you can find out the change in potential energy. If you know the initial kinetic energy, you know the final kinetic energy. As energy is concerned. This is pretty much review for it. So then if we have V, if I show you how do we calculate E? If I give you the potential at 2 points and we want to estimate the electric field between those 2 points, how would we do that? Do we have can we do that? It's 10 volts here and it's 0 volts here. Can I figure out which direction the electric field is? Which way is it heading? 10 volts here, 0 volts here. Electric field goes from positive to negative, so electric field's going from the 10 to the 0.
That was impressive.
The change in voltage is 10 volts, and if the distance were half a meter, then we'd expect the field strength in that middle there to be around 20 volts per meter, or 20 newtons per coulomb. So one of the exam questions last year that people really struggled with is looks something like this. These actually got farther and farther apart. I had point F, point E. Now what did I ask here? Sketch so my electric field lines on this graph. What would you do? Which direction do they point? Positive to negative. How do they cross the equal potential lines? Perpendicular. So I expected something along the lines of with arrows. What is the electric field, electric potential at point E? 20 volts. It really can be that. What is the electric field, E, at A? How on earth can you figure that out? What's a little bit more information here? We had 0.5, 1.0, 1.5, 2. find the electric field at E?
Try taking the change in voltage over change in distance.
You can look at the change in voltage over change in distance. So if we measure this distance from here to here, then we could say that's a 20 volt change. And then we could measure the distance, and we can find the magnitude of the electric field at that point in time, at that space. And then we can, but to find the actual vector, we also have to find the direction. So you could estimate that with the rise and run. The other way you could do it is you could find the x component of the electric field by the change in the electric field in the x direction. Again, 20 volts over now, what is this? 2 meters. So that's about 2 volts per meter in the x direction. And you could look at the change in electric field in the y direction. And you could find Ex and Ey that way. And you should find about the same thing as you found the other direction. If you had lots of times, you could do it both ways and average them, but that's more work than you have on an exam. Either way, I accept it. But you did need to have both a magnitude and a direction. You could have done that by a magnitude and an angle, or an x component and a y component. Questions about that? This is probably the question that gave people the most trouble on the exam last year, which is why I want to cover it here. What is the electric potential energy of a 5-gram particle with a charge of 0.2 microcoulombs at C? So we have a particle with mass of 5 grams. So mass equals 5 grams. U equals 0.20 microcoulombs at C. How would we find that? And what we want to find is electric potential energy. There's a red herring here. What is it?
Grams.
The mass. You need the mass to find the electric potential energy. No. So I am fond of doing that. What that does is it, for the people who look at what variables there are and then go hunt for an equation that's in them, that this isn't helpful for them, make sure you actually have to understand what's useful and what isn't useful. So oftentimes I will give you information. I might even tell you it's a red ball. Some of the information I put inside the questions may not be useful. So we don't need the mass. To find the potential energy, we know that U equals QV. In this case, substituting Q, we know that at C, V equals 20 volts. Or, I'm not sure. I might do something different on the graph. On my graph, it was 25 volts. Substitute in, you're done. So it really was fairly straightforward. Rank the following 3 quantities from largest to smallest. Work AB, work BC, and work EF. For, let's see, in all of these, it was a 5-gram particle with -3, the same charge. So I'm moving something, the same charge from A to D. A to,
You have A to B written.
do I have A to B written there? I'd like live, it should be A to D. And the charge here now is negative 3.0 coulombs. So it's a negative charge. So I'm moving from A to D, B to C, and D to F. So how much work is done from B to C? 0. From A to D we have negative 3.0 coulombs. And our change in voltage is what? We go from A to D. A was about, I don't know, 28 volts. To D, looks like about 17 volts.
38.
38 and 20.
What's that?
It's just different.
It's different. Unfortunately, it's different on this. So how would we calculate it? We'd figure out, say, 38 volts, 24 volts. We go from A to D. What is our change in voltage?
14.
Positive or negative? Negative. From 38 to 14. So this would be positive 42 coulomb volts. And then E to F you'd calculate it. Does that make sense? If we move a negative charge from here to here, it would be positive work. What do you think's located right about here? Positive charge. So if I move a negative charge away from that positive charge, that would require positive work. That doesn't make sense. So then you'd rank them. Does that make sense in terms of approach? I could also have given you mathematical descriptions of these, in which case you just take the derivative of the integral. I suspect that most of you can do that better than the graphical. I thought this was meant to be a really easy question last year. It just blew people up. So, you ready for that? I do want you to be able to visualize, but I can also give you the mathematical description to go with it. I could say that V equals 3R cubed, and ask you to calculate E at some place. So what is E at R equals 4 meters? So then how would you do that? E of R is equal to what? Negative dV dr times R hat. So you take the derivative, negative 9R squared R hat. Now you substitute in 4 meters for R. You're doing the same thing graphically up there, going back and forth. Just that I think you're more comfortable with the math than actually doing it without the math. Any questions? All right. Then we get to Ohm's law and resistance. I think if I gave you the geometry of an object and the resistivity, you could calculate the resistance of the object. If I gave you the voltage across an element and its resistance, you could tell me the current through it. If I gave you the resistance and the current through it, you could tell me the voltage across it. And the most complicated of worlds, I could ask you to do 2 loops. What I done in the past is I gave it a circuit with 2 batteries, 2 loops. I didn't ask students to solve them, but I asked them to give me 3 equations. One to draw the pot. It's very important if you get a problem like that. If we get one of these problems, B1, R1, R2, R3, P2. If I ask you to draw the equations, make sure first of all draw your loops. Loop 1, loop 2. Draw your positives and negatives. Now I know what your loops are. Make sure you draw your loops, draw your current. Now, what would your 3 equations be? The junction law we could either do here or here. I'm going to do it here. So our junction law would be our ins equal our outs. And I could do loop 1. Loop 1 would be V1 positive minus I1 R1 minus I3 R2. That all equals 0. And loop 2 would be the same way. I'm not going to ask you to do the algebra. So I give you a problem like this. Any questions about what I'd expect there? I pushed circuits a little bit more this semester, so it's more like if I was going to have any change from last year, it'll be that there'll be more circuit questions in the past. If I gave you a network of resistors, could you find the equivalent resistance? So, now be careful. What kind of tricky things could I do to you with circuits? Squares, weird angles. I could give you weird angles. Yes.
Probably all works. Little zigzags.
If I give you this circuit here, what do we notice about all those resistors?
They're all in parallel.
They're all in parallel. They have the same voltage across them, right? This is the same potential difference. So if this is R1, R2, R3, R4, we know that 1 over R equivalent because they're all in parallel. So don't let me trick you with things like that. If you want, we can straighten these up, can't we? But that doesn't change the circuit. Straighten it up, it's still in parallel. But that's not the only way it can be tricky, right? I could do something like this. Now what's going on?
Two parallel circuits.
How would we, let's call this R1, R2. Are these all in parallel?
No.
Are they all in series?
No.
No. Which two would we go after first? R3 and R4 because they're in parallel, right?
They're in series.
No, they're in series. The current that goes through one goes through the other. So those are in series. So we combine R3 and R4. I'm going to straighten this up because that's silly. And then this is R3 plus R4 because they're in series. And from here we can analyze if these two are in parallel. Once we combine those, they're in series with R1. And capacitor circuits. What do we know about a capacitor if it's been in a circuit for a long, long, long time? In a DC circuit. There's zero current through it. Does that mean the potential across it is zero? No, the potential across it's unknown. What if a circuit has been, the capacitor is, we know the potential across it, say it's been discharged, so the potential is zero, and we close a switch. The instant that switch is closed, what do we know about the capacitor?
Access the
The
battery.
instant after the switch changes, closes, or opens. What does not change? The charge inside that capacitor doesn't change, so the potential doesn't change. Now, could the charge be changing? Could there be current flowing in or out of the capacitor? Definitely. So, if it's been a static situation for a long time, and now we close or open a switch, what we know is the instant after that switch is opened or closed, that the capacitor's potential, the charge in it and the potential across it hasn't changed, but the current, there could be some current in it. So the situation is after a long, long time, the charge inside the capacitor is fixed. It's not changing. But there could be some charge in it. But we know there's no current because the charge in it's not changing. So, the second hardest problem from last year looked like this. The switch has been open for a long time. What are the currents I1, I2, and I3? Well, that better label them, hadn't I? The switch has been open for a long time. What are the currents I1, I2, I3? switch is open, there's no current flowing through anything. What's the charge across on this capacitor if the switch has been open for a long time? Zero. And there's a path for the charge to discharge, right? So definitely, in this case, there's no doubt that there's zero charge in that capacitor if that switch has been open for a long, long time. Any questions about that? Now the switch is closed. Immediately after the switch is closed, what are the currents I1, I2, and I3? Immediately after it's closed, we can treat this as a wire. What's the charge in this capacitor the instant that that switch is closed? So what's the potential across it? 0. What's the potential across this 8 ohm resistor? What's this potential right there? Across the capacitor? 0. So isn't that the same potential that's across the 8 ohm resistor? So if there is 0 potential across the capacitor, there's 0 potential across the 8 ohm resistor. What's the current I3? 0. The instant this switch is closed, the current through that 8 ohm resistor is 0. What is the current I1? Let's take a loop law. Let's do that. Actually, let's do this loop 2. Call this loop 1. So this is B, the instant after it's switched. Loop 2, we know that we have 0 volts, VC minus I3 R 8 ohms equals 0. VC equals 0. That implies I3 must be 0. So, like Carl said, the capacitor looks like a wire. The current that's flowing down flows through the capacitor, not the 8 ohm resistor. What is loop 3? We have 12 volts up. Let's draw a positive and a negative. Minus I1 times 4 ohms minus VC equals 0. But at first, VC is equal to 0. So this becomes 12 volts minus I1 times 4 ohms minus 0 equals 0. I1 equals 3 amps. So what is I2? Let's look at the junction law right here. We know our in I1 must equal our out, I2 plus I3. I1 is equal to 3 amps. I3 is equal to 0. So therefore, I2 must equal 3 amps. So just like Carl said, this acts like a wire. We have 12 volts across 4 ohms.
Is that because it's choosing to go the path of no resistance?
Current does choose the path of least resistance. In this case, there's no resistance through the capacitor initially. It looks like it, right? Now, there's actually never resistance through it with capacitor and a real capacitor. Now, if we had a 2 ohm and an 8 ohm, the current splits, but more current goes through the path of least resistance, lowest resistance. In some sense, this acts like 0 potential, 0 resistance initially. After a while, the voltage starts to build up because we have charge flowing into that capacitor, so after time, the voltage will build up. So that comes to the next question. The switch has now been closed a long, long time. What are I1, I2, and I3? After a long, long time, what do we know? We know the current to the capacitor becomes 0. What do we know about I1 and I3? I1 equals I3. So therefore I1 equals I3. We don't know what they are yet. I could do a loop 1, and I don't know I1 or VC, so it's true, it works. And I can do a loop 2, and again I have I3 and VC. So then I had 2 equations and 2 unknowns, and some students did that and they solved the problem that way. Well, actually most students did it that way. We succeeded. But there is an easier way. Instead of doing loop 1 or loop 2, how about if we do loop 3, which goes this way? Joshua.
Can you relabel your equation from loop 3 earlier?
What's that?
You wrote it as loop 3 earlier.
Oh, I did do that. I don't know why you did that.
Loop 1.
Now it's about loop 1?
Now you have 2 loop 2s.
All right, I wanted loop 1 to be, okay, I wanted that to be loop 2. I wanted it to be loop 1.
Thank you.
So I apologize. So, loop 3 now, I only have one unknown because I1 and I3 are the same. Loop 3, this time I really mean loop 3. 12 volts minus I1 times 4 ohms minus I3 times 8 ohms equals 0. But I3 equals I1. So I can say then 12 volts minus I1 times 12 ohms equals 0. I1 equals I3. What's the voltage across the capacitor? No. Let's go back to loop 2. Loop 2. VC minus I3, 8 ohms equals 0, but I3 equals 1 amp, so VC minus 1 amp, 8 ohms, 0. VC equals 8 volts. So if we think about it, there's 8 volts across here, 4 volts there, that's 12 volts, it makes sense. Could I now ask you the charge on the capacitor? We know that the charge over the capacitance equals the voltage. So we know the voltage, we know the capacitance, we can find the charge. How are people feeling? Super, I still need to work some. Yeah, I need to work a lot. Would you like to go over the conceptual questions?
Yes.
All right, that's a definite yes. Should I? All right. Electric field A is always tangent to an equal potential surface. Is always perpendicular to an equal potential surface.
Is there always put this on like the projector so you can
I can get it up. It'll take a second to get that going.
So I'm telling you, there's no way I'm going to remember 8 meters.
All right. Well, we can go over them one at a time. Well, this is coming up. Is it true, let's just go over these one at a time, that an electric field is always tangent to an equal potential surface? Definitely. It's going to be tangent? No. It's perpendicular. Definitely not tangent. It's definitely. It bisects an equal potential surface. It bisects an equal potential surface. Really?
It doesn't have to.
No, it's perpendicular at all points. It doesn't have to bisect. As a matter of fact, the electric field is everywhere, so it's not bisecting.
Every sex it?
Every sex it. I don't know what that means.
Multi-sex.
So, makes an angle to an equal potential surface that depends on the amount of charge.
Oh.
No. It's an interesting law, but definitely not anything wrong with that. Sure. None of the above are always true. False, because one of them untrue. All right, then the next one. I have 3 batteries. Let's examine this. All right, those. What potential? Oh, that's not very useful. Do you guys like this? Yes. This is good? Yes. Okay. What potential difference is created by these 3 batteries?
5 volts.
Let's see, we have, starting from here, plus 3, minus 1 is 2, plus another 3 is 5 volts. The tricky thing there was the middle one was not 3 volts. Any questions? Why people would do that, I have no idea. Consider the electric field created by a positive point charge. Consider the positive charge the source charge. A particle with a negative charge is moved closer to the positive charge. Which statement best describes the negative charge? Before you even look at them, as you move the negative charge closer to the positive charge, what happens to the potential? Does it depend on the charge?
No.
Of the charge of interest that's being moved? No. The source charge determines the potential. What about the potential energy? Does it the charge of the which charge matters? The source or the charge of interest?
Yes.
Both of them, right? So, we're moving the negative closer to the positive. What's happening to the potential? It's going up as we get closer to a positive charge. The potential is going up. What about the potential energy?
Decreasing.
It's going down. You got to get the sense that I might ask you something like this on the test?
Yeah.
All right. A 100 ohm resistor is made of a cylinder of carbon. A second resistor is also made from a cylinder of carbon. However, the second resistor is twice as long, and the radius is twice that of the first resistor.
Is this on the equation sheet? There's something weird with that. I don't know what resistance.
Okay, remember, I do think it shows up on the equations. So, let us get the equation sheet because we're going to remember it. A resistance now. Let's just see if we can, what would you expect first, before I even write the equation. I want you to think about this. If we double the length of the cylinder, what's going to happen to the resistance?
Double.
Go up by how much? Double. If I change the radius, what have I done to the surface area? I've made it bigger. If I double the radius, what happens to the surface area? Goes up by 4 times, right? Yeah. 4 times, right? So if I double the resistance, the area goes up by 4 times. As I increase the area of our resistor, what happens to the resistance? It goes down, right? Think of the pipe's bigger.
50 ohms.
It's 50 ohms. So if we want to go to the math, it is, I don't memorize these equations. I'm guessing it's the resistance times the length over the area. What? Resistivity. I think I have it. If not, I do want to add it because.
So we're not.
All right. Oh, there it is. Resistance equals rho times L over A. It's also equal to L over the conductivity times A. But you really don't need to look up the equation. Think about it. Think about what makes sense.
I don't know what the field is, but
3 metal spheres of different radii are connected by a thin metal wire. Which of the following is true concerning the potential and electric fields at the surface of each sphere? Oh dear. We did this with 2. If conductors are connected together, what do we know about the electric field or potential? Or both? Inside the conductors, what do we know about the electric field? 0. Is the potential 0 then? No, the potential is what? It's the same everywhere. Okay, so what do we know about the electric field and potential of these 3? They all must have the same potential. All right, so we've eliminated A, B, and D. So does that mean the electric fields are the same? No. If you go through the math, you can find out the electric field is greatest at which one? What do you want to hold over your head?
The lightning rod.
Sharp pointy object, because the electric field is greatest where the curvature is the highest. So the smaller the radii, the higher the electric field. You can convince yourself that if you look at the electric field for a point charge or a sphere, the electric field is proportional to KQ over R squared. And the potential is proportional to KQ over R. So that means that this is proportional to V over R. This electric field proportional to potential is proportional to. So as the radius gets, for a given potential, as the radius gets smaller, what happens to the electric field? It goes up. So the math's fairly straightforward if you look at point charges. And you know that, right? No pointy objects over your head in the language. That's the way to remember this. Electric fields get stronger for smaller radii, for smaller, very small radii. So if you have a pointy object, you get a high electric field out of it. That helps the air to discharge. That's bad if you're in an I think that was the answer. That was 2 years ago. The electric field, which is a vector quantity at every point in space, may be determined from an electric potential, a scalar quantity at every point in space. Is that true? That's definitely true. May be used to determine the potential difference between any 2 points in space. So if I give you the electric field at every point in space, can you find the potential difference at any 2 points in space? Well, if you can find the potential at every point in space, you certainly should be able to find the difference potential at every point. So definitely. May be measured in volts per meter or Newton per coulomb, which are equivalent units. That'd be true too.
D, all the above are always true.
False.
That's true. D, none of the above are always true. That is the one that's not. So the best answer is
C.
a small charged ball is accelerated from rest to a speed v by a 300 volt potential difference. If the potential difference is changed to 1,200 volts, what will the new speed of the ball be? I think I may have screwed this one up. What is the change in potential energy? 4. Kinetic energy is a function of velocity squared, so the velocity must be twice as big. So the answer is 2v. So it did work. Do you see how you reason it through?
No.
Okay. Potential energy. So we're going to assume mechanical energy is conserved. So our change in potential energy would be proportional, equal to Q and delta V. If delta V becomes 4 times as big, that means we have 4 times the change in kinetic energy. So in the first case, we have 1/2 m velocity squared equals delta UE. In the second case, we have 1/2 m v2 squared equals 4 delta UE, because we have 4 times the potential energy. That means V2 must be twice as big as V, or V2 equals 0. All right. 2 wires are made of the same material, have the same length. So this is going to be another one of these. And I'm going to let you go because it's about out of time. Are there any just immediate final questions before we go?